All
right.
Rotate laptop. And okay, so yes, let's start with the recap of the discrete phase formalism. Just for simplicity, we consider the case of fields FP, where we consider phase spaces, discrete phase spaces, with P that is prime but odd, because in the even case we just conceptually everything is the same, but we have to take care of some technical complications. And the idea is that we want to basically do what we do in the, for example, for the bosonic phase space. So namely, when we work on the continuous phase space, and here we can define basically the displacement operators that, just for simplicity, I write in this form, where these Q and P are just canonical position and momentum operators. And yeah, we want to do the same in the discrete setting. Sorry. Okay. And the idea is that to do this, we need to introduce a technical tool that is the discrete Heisenberg group that we denote in this way. And this is a group of triples with this composition. Sorry. Yeah, it's a group of pairs. Let's write in this form, where the composition rule is this one. So the first pair is just the addition, while in the second pair we have the an additional term. Here we have that V and W are elements in the discrete phase space. T and S are elements in the base field. And this object here is the symplectic form. So this is written in this way: Vi Wn plus I minus Wi Vn plus I. The reason why we need this group are basically two, I think. The first one is that we can consider the E-reps. We can classify the E-reps of Hn. And in particular, these are operators W of Pt that when acting on some function f of x are defined as well, we have f of x plus vx, and then there is a character where we have t plus v 2 to the minus 1 vz vx plus vzx, where just we are using the decomposition of v as vz vx, since this v is an element of phase space, right? So, and this you can imagine as being just split in position and momentum coordinates. And this chi is a map that is called the character, and this is a map, sorry, from the base field to the unitary circle, and this is such that an element T is mapped to omega T, where this omega is just the root of the unity. So, in this thing here. Yeah, for the Heisenberg group, we have this. One can prove that these are the only irreps, and in particular, if you want to be precise, these irreps here depends on the character we are fixing for the base field, and then one has Stonefan-Nonna's theorem. And basically, these say that if we have two irreps, let's say rho and rho prime are irreps of the Heisenberg group, which agrees on the center, namely they have the same character, then rho and rho prime are equivalent. And another fact that is interesting here is that we can retrieve the irreps of the phase space, and these are just discard the T coordinate, so we just stay as an irrep of phase space, right? The composition, and this is just W of Vz Vx0. The difference when going from the Heisenberg group to the phase space is that these are not these are projective representations. So when you consider you don't have a proper homomorphism property. So so to say, this is something like W of V plus W. This is only proportional to W of V, W of W, and there is here okay, there is a phase factor that I can also write that is just given by the character of -2 to the -1, and then there is this form appearing here. While if you look at these representations on the level of the Heisenberg group here, so when you still have these coordinates, then you have you don't have these additional factors. But yeah, in the end, we are interested on the phase space level, so we have to remind of this fact. These irreps, another thing is that they naturally factorize. Namely, we are considering the phase space fp to the 2n, but this is just fp squared plus fp squared, and this sum is of course n times, and accordingly we have that W of V is just W of V1 tensor W of Vn. Where we have okay, I'm just to make things clear here. This is V I'm writing as V1 Vn, but here we have that V high is just Viz Vix. So we have two M coordinates. And okay, that was basically the first thing that we looked for the Heisenberg group. And secondly, we looked at the center fixing automorphisms, and we observed that they have a particular form. They have to satisfy a particular form, but the interesting part was that basically the only maps that makes the center that preserve the center are linear transformations and symplectic transformations, and these things are interesting because of Donfanon's theorem, because this means that we are just considering maps that transform between equivalent representations. And so the idea is, if we want to write formally what Donfanon's theorem says, is that if rho and rho prime are equivalent, that means that there exists a unitary operator U such that rho prime is just U rho U dagger. But yeah, this U can be is basically generated only by linear or symplectic transformations, and in the case of odd characteristic, so to say, one can write this U to be just operator mu that depends on G and V, where this G, is a symplectic matrix. And V is a point on the discrete phase space. And yeah, but the thing is that in this case one can also factorize this map, because for non-even fields, you have that the center fixing automorphism center fixing automorphism group is just the affine symplectic group, which has a semi-direct product structure. So it's basically symplectic maps, and then you have these linear maps that can be just represented as fancy spaces. So yeah, we can just write this mu of G as mu of G, which is a representation of the symplectic group, and then there is a Y operator. Okay. Oh yeah, and okay. In the even case, to make things simple, everything works kind of the same, but one has to take care of some additional phases. Namely, we have to tweak the definition of the Heisenberg group here. We cannot choose anymore this object, and instead we we need to introduce another function that just because we cannot consider these additional coordinates to be in F2, but we just need to extend to Z4. Maybe just let me write that. Makes things a little more clear. So when P is equals to 2, we have the Heisenberg group is just the group of points in the discrete phase space, and then we have Z4, and then there is the formally the expression of the composition law is kind of the same, but we don't have the symplectic form, but another function beta, which is such that when you take beta mod 2, this is the correspond to the symplectic form on F2 to F1. The main consequence of this fact, and okay, so that's the difference basically, but some phenomenon's theorem holds equally the same in this case, and still you can define this W operator as before, and from this you can just get the while operators on the discrete phase space to be projective representations. And yeah, they are still characterized by their center, basically, so by the choose of the character. What is different in this case is the structure of the center fixing automorphism group, because it's not true anymore that you can write that as a semi-direct product group. So yeah, that's the annoying thing. And that's because you just need to take care of some additional phases. These phases are basically coming from the fact that one has to satisfy a compatibility condition. And so to say, yeah, this beta must be such that you have beta of GB GW minus of beta of VW must be equals to some function alpha of V plus W minus alpha of V minus alpha of W. Yeah, this function here comes from some general considerations for the structure of the center fixing automorphisms of the Heisenberg group. The interesting thing is that in the case of odd characteristic, you can choose that to be 0, and this is not the case anymore when we consider the qubit case. And yeah, but from this condition here, one can prove that G still must be symplectic. And yeah, this function alpha can at least be fixed on a basis because it's not unique. So that's this is I think was kind of 1.5 meeting before. If there are any questions. Otherwise, I go. I change
have
topic to
a small question about this sort of decomposition that you mentioned about like a semi-direct product thing.
Yeah.
Is that like how in continuous variables, like bosonic modes, you have Williamson or what's that called, like Bloch Messiah kind of decomposition, like symplectic and then displacement, like that?
Is not really the same, because that is more about only the symplectic part, right? In the bosonic case. But yeah, it's like in the bosonic case where you just think at yeah, you have a displacement, right? And then you map to another displacement. And how can you do that? You can conjugate with another displacement, right? So I don't know, just being super sloppy here. And this would be coming from this term, right? Otherwise, you can conjugate by a symplectic matrix. That means, for example, you are applying a squeezing or a beam splitter or this kind of transformation. These are in the symplectic group, and yeah. And
so like a quadratic Hamiltonian, yeah.
Yeah, exactly. So but these are the transformations that belongs to the symplectic part of the of your interfixing automorphisms group. But yeah, it's like this term here on the right is kind of the trivial one, because we are representations. It's not really trivial, but it's trivial that this equation here is true in this case. So, and yeah, it's in the previous case it's just more complicated to write things, because you don't have this you cannot factorize in this way. But in the end, it's something that you can still take care of. It's just that you need to almost force some additional phases.
Yeah, I think you were mentioning before. And this mu of G, will you be showing us how to construct them then, or
no, I won't. But it's like, for example, you can do that for the generators of the symplectic group, right? And actually, this is what you do in the qubit case, since it's slightly harder to deal with that, because you cannot write these things, but you can do that on generators. And actually, you can find the explicit forms. I think there are on Marcus' thesis, but I should check.
Yeah. Okay.
Yeah, I will not show them because they are kind of clunky and long expression.
Yeah, it's a bit technical. Yeah. Okay.
Yeah.
Okay.
Okay, so I think we can go to the Clifford group and just do a little recap here. Yeah, let's say we still consider only the odd characteristic case, just for simplicity. And actually, in this case, the definition is very simple, because we just start again from this this thing here. I'm changing notation. That was the group that preserved the center of the Heisenberg group. So is this group here, and now, and yeah, we had this expression here. So this thing was just mu of G W of W, or W of V, sorry. Actually, something that I did not mention before is that this mu of G, at least as general definition, so this is W of G P. So if this mu of GB can also be written as W of GB mu of G. But since we have this nice decomposition, now what is the Clifford group is just the basically is the same as the center fixing automorphism group of the Heisenberg group, but now translated at the operator level. So we just need to use these maps mu and W to transform these the objects here into unitary operators, and in particular the Clifford group would be just the image under mu of the symplectic group, and now you have product the image sorry is out, yeah, sorry, the image under W of the Heisenberg group. And yeah, so basically this is the case for the odd case. And the one nice thing that we could list here are the generators for the Clifford group. And so now it's like the same as we know in the qubit case in the usual language, let's say. So we first have the Z operators, and these are just the sum over elements in the in FP, and we have the character, sorry, and then we have this thing, this operator here. And then we have the X operator, which is kind of, yeah. And in this case, we have X plus 1 X. And these are basically the generators for this side. Of course, under the action of W. And now the same could be done for the first factor. And the idea is that one could just take the generators of the symplectic group and transform them with this map. Something that I will not prove, but the nice thing is that you retrieve the generalization of standard operators. Namely, first we have the Adamar transform, and now we have sum over 2 elements, and here we have a chi of X times Y, and then there is X, Y. Then you have the C naught operator, namely X, Y, and here we have P squared, we have X and X plus Y, X, Y. And then there is a phase operator, x, and well, just for completeness, another operator m of lambda, which is kind of a direction. Well, I'm just listing these operators. But yeah, the thing is, if you these operators are generators also in the qubit case that I just mentioned soonish, because one can prove that one can construct the Clifford group in such a way for qubits, of course, in such a way that these are generators. But yeah, if you specialize this expression in the case of p equals 2, then you retrieve the, for example, this operator here would be just the standard data mark. So you will have something like this. I'm not sure about this minus sign here, but it is somewhere anyway.
And for qubits, conjugation by Hadamard of X gives you also Z, like in the qubit case?
Should be. Well, we could do that for exercise. I think.
Risky exercise.
Yeah.
But yeah, we could try next week maybe.
Yeah, why not? But yeah, it's something that given these expressions, you can play however you want, because you know how the byte operator is acting on these things. And yeah, and then you just, for example, for the Z operator, that will be just taking W of Z0. This is the Z operators in the qubit case. And see what's happening.
Wait, can you say that again? Sorry.
Yeah, it's because okay,
I
you
think
have these
last week.
things, right? You have this W of VZ acting on a ket X. This is just omega to the VZ times X. And then there is also plus 2 to the minus 1 VZ Vx. And this is X plus Vx. This is the general definition. But let's say a Z operator would be just W of VZ0. And so Z of VZ acting on X is, yeah, so you don't have this term here, it's just omega to the VZX X.
So you were writing this down for the Heisenberg group, but when you're doing this here, it's more like without this T is added.
Yeah. It's like you forget about the T because you know.
Put T to 0, yeah.
Yeah, the Heisenberg group is useful. The idea is that the Heisenberg group is useful to arrive at this object, but when you have this, because it's just a technical tool to define your generalized displacement as you do in the continuous case. But yeah, you just use these kind of properties, and then you can see what's happening under conjugation with the Hadamard, for example.
Okay.
I want just to mention what's happening in the yeah, it was P not 2. In the case P equals 2, yeah, the thing is that these two equations are not true if P is equals to 2. But and so you don't define the Clifford group as in this equation here, so because you don't have this nice structure. But actually, you can do another some technical considerations, and the idea is that you still define the Clifford group as the group that is a normalizer of the while operators or the Pauli operators, and in such a way that the generators are basically the same. So these ZX are coming still coming from the Heisenberg part or phase space part, and these others are still generators of the symplectic group in characteristic 2. The only difference would be in this S operator, because here you would have, let's say, it's kind of the same formally, but you have a character over Z4 of X squared. This is for qubits. But the other definitions are exactly the same. And yeah, in this case, if you restrict yourself to the right number of the right hand, then you retrieve exactly C naught or whatever. But yeah, the important thing is that we still have the same generators, and yeah. Okay, if it's okay, I will go now to stabilizers and finish what we started last week. Well, last time. Well, once again, suppose P is not 2. What we want to do now is to consider a subspace M. Well, yeah, sorry. Which is isotropic. To remember what does it mean is that if you consider orthogonal, this is the group of elements E such that for each W, such that BW is equals to 0 for each W, and then you have that M is contained in M paired. Now, if you consider an isotropic subgroup, subspace, sorry, of the discrete phase space, now you have that M times 0 is an abelian subgroup of the Heisenberg group. And this is kind of obvious because you have that the non-commuting part in the T term of the composition of the Heisenberg group is 0 by definition here. Okay. So let's now what's happening here is the following thing. Since this group here is abelian, in principle one can consider the representation of this group, right? I'm just writing of M, but yeah, B of M times 0. But one knows from group theory that this representation is reducible, and this is a consequence of Schur's lemma. And in particular, the only because the only irreducible representations of an abelian group are one-dimensional. So to say that the irreps of M are just characters, the kind of the maps introduced before. And they are just phase factors then. Now the thing is, once we have this thing, the idea is that this representation here, this means that this is reducible, but yeah, we are considering finite groups, so this is completely reducible. And that means that this is can be written as a direct sum of irreps. Yeah, I forgot to formalize this one. So I'm being sloppy here again, but it's something like this. So this would be a direct sum over characters, and then you have these characters, but they can appear with multiple time in this decomposition. So you have kind of so you take the tensor product over the identity multiple over a lambda times, and this would be just that these characters is appearing in this decomposition lambda times. The idea is that when what is meaning for this completely for this reducibility condition is that W of M is just block diagonal, so it would be a matrix like this, and so on. And yeah, and some blocks are appearing the same way given these things in this expression. And now one can consider what is called the isotopic component of this decomposition. Namely, it's just the direct sum of all the psi. It's the direct sum over all the copies of the same irrep. So yeah, and this space, so that's called, namely, this is just a space that can be denoted in this way. So because it's fixed by this character that is appearing many times in the decomposition of WM. And we can basically find the dimension of this subspace because if we define this operator here, this is 1 over the cardinality of M, and then we have sum over all vectors in M, and we consider psi of B complex conjugate, and then we have W of B. Then one can prove that this is a projector, and actually is a projector on C of M xi. That's yeah. And so one knows that if we want to know the dimension of C, this is just the trace of this projector. And this trace is actually easy to evaluate because all the while operators are traceless, except the identity. Just think at the qubit, x, z, and y are all traceless, and you only have the identity that is was traces too. And the same is by definition for all while operators. So this is just trace of the identity over the cardinality of M. And so this is just P to the N, that would be the trace of the identity. And then we have minus the dimension of M as a subspace. Okay. And yeah, when you take M to be of dimension N, so it's, well, in symplectic language, M is a Lagrangian subspace. Then the dimension of this thing is 1. So it's spanned, this space is spanned by only one vector. And then you call this vector stabilizer state. Just to remind the remind of this Lagrangian thing, we have that M is isotropic, and if M, the dimension of M is equals to 1, then M is Lagrangian. And the canonical example is the are the, for example, only the position subspace. So it's just, for example, Z1. Sorry, just VZ1, VZN, and then all zeros. And the same is for the other subspace, for example. And actually, these are the decomposition that we are usually using for the definition of while operators. But yeah, actually, this is the way you would introduce stabilizers in this with this language. Okay, and yeah. Now, in principle, I think I would just go to discussion of a kind of a general. Sorry, I forgot to mention what's happening in the qubit case. In the qubit case, again, we have to modify things at the roots, namely, it's not true anymore. These sentences, this sentence here, it's not true. But what one can consider for qubits is a slight generalization. So
Mirko, sorry, I was considering the definition of the Heisenberg group now.
Yeah.
And I don't really see that it's abelian from the definition, because I still have this kind of.
No, the Heisenberg group is not abelian.
Yeah, but if I put S and T to 0, so I use cross 0.
Yeah.
I don't see that this is abelian, because still I have like this fat term there. Or
no, you don't have, because if you take V and W in M, now and then you consider this, well, just take 0, for example, but it doesn't matter. Now you have, the first term is abelian, right? And the second term, 0 plus 0, and then you would have 2 to the minus 1 VW, right?
Yeah, and now what happens if we swap?
This is 0 because M is isotropic. It's by assumption. M
is isotropic.
Yeah. It's because then means that you have this condition here.
Ah,
Yeah, that's why I said it was.
okay.
Yeah.
So okay, so I missed that it's needed that it's isotropic, and that condition makes it an abelian, yeah?
Yeah, of course, because the symplectic formula is antisymmetric, right? So, but you basically taking the isotropic condition, you are just saying, okay, we can cancel the symplectic product.
All right. Okay. Thank you very much.
Yeah, sorry.
So
Probably I would mention.
we were saying that this abelian condition for the qubit case, that's a complicated one.
Yes, because in the qubit case here, you would not have this thing, but you would have that beta function, right? And so let me just go back to the definition. So for qubits, if we consider again the product, this would be V plus W, and then yeah, T plus S plus beta of VW. And now the thing is that one can play with the properties of this beta. Because we say that beta mod 2 is just BW, right? Now, if you take V and W in M, that means that beta mod 2 is equals to 0 because M is isotropic. That means that basically there exists a beta bar such that 2 beta bar is equals to beta, where this beta bar is F2 valued. And and also one has that beta bar of VW would be equals to alpha of V plus W minus alpha of V minus alpha of W. This was still coming from the discussion of the Heisenberg group for qubits. And now basically we just need to modify the definition we considered before, and actually you would consider the group M alpha, that is just the group of elements of B and then 2 alpha of V, such that V is in M. So let's say M is isotropic. And this is a subgroup of the Heisenberg group. And actually, now this is again an abelian subgroup. We can check that in principle. So yes, you take V and 2 alpha V, and then multiply by W, 2 alpha of W. And this would be, well, V plus W, and then 2 alpha V, 2 alpha of W. And now there would be beta of V plus W, right? But this beta is just 2 beta bar. So this is the same, and now we have just being very explicit. And but now you can just apply this expression here for beta bar, and then the terms alpha of v and alpha of w will just cancel, and you are left with alpha of v plus w, which is it's abelian, so to say, and so this group is abelian. And then you do the same kind of considerations as before. So you have an abelian subgroup of the Heisenberg group. So the representation, the while operators restricted to this subgroup can be decomposed into irreps, and you will introduce these stabilizers in the same way. So you will just consider this projector onto an isotopic component, and taking the dimension, if you have a stabilizer state or actually stabilizer code when you don't take a Lagrangian subspace. And the other difference is that here we have this dependency from this function alpha, which is not really unique, but in the end you can just set you can just fix this function on a basis, and for example, you can just force this function to vanish on the standard basis, and then you will retrieve some kind of it would be unique again. But that would be again the prescription for qubits. And okay. So actually, this is the way you just introduce stabilizers. The idea is that you have these projectors, and you can describe stabilizers just looking at these projectors. And for example, you are able to compute the overlap between two stabilizers, right? Just looking at the two projectors and taking the trace of their product and see what's happening. At this point, you can do many things, but things are kind of quite technical in the calculations. We can do something. Now I was just thinking to go to the simulation task. That is kind of easy given all these tools.
Can you just explain me one more thing, please? This beta dash, you said that this will be F2 valued. I'm a little bit, I think, lost in. I mean, doesn't it always have to?
No, the idea is because since you have that beta mod 2 is equals to 0, right? The idea is that you can find a beta bar that is F2 valued. Why is F2 valued? Because when you take 2 beta bar, this is automatically 0 by default.
So beta bar will become on different arguments either 0 or 1, and then I multiply 2 and I get the 0 mod 2. But we are talking about qubits, so I don't do addition mod 2 anymore, or?
It depends on the cases. In principle, this beta, in principle, you don't, because beta is mod 4, right? But you still have this.
Is mod because of the Z4 factor in this?
Yes.
Okay. So
I mean, your phase space is F2, so you do addition mod 2. But when you go to these phase factors, you need the mod 4 because you need the I. Otherwise, you wouldn't have the Y operators in this
Okay,
description.
so because we have the Z for the construction of the phase space, beta can map from F2 into Z4 or F4 or whatever, something like this.
Yeah, actually, yes, beta is mapped from F2 to N times F2 to N in Z4.
In Z4, yeah, because it pops into this Heisenberg argument.
Yeah, exactly.
Okay.
So, and actually, yeah, you always have to take care when you have things that are mode 4 or mode 2.
Mhm.
Yeah.
Yeah, I was guessing that it's very non-trivial, but I didn't know why. Okay, thanks.
Yeah,
Yeah.
no
So
problem.
okay, let me stop maybe, and
Okay.
we will have one video. Thanks so much for the stabilizers.
Thank you too.